Okay, so go ahead and pass up the homework that's due today. Again, not the graphing calculator activity. This is the reflection questions that were originally assigned last Wednesday that I said I was going to pick up today. Should look like this. Pass them on up. While you're passing them up, let me talk about the exam that's Thursday. So I've posted a new menu item here, quizzes and exams on Blackboard. And so if you go there, you'll see exam 1 and associated quizzes. So there's 2 items there now. One is just a bullet point outline of what's covered on the exam, which is basically everything we've done so far. Make that a little bigger. So ideas and meanings of multiplication and division, representing covariant quantities visually with the horizontal bar diagrams, and then how we get an XY graph out of that. And then we move to representing this covariant quantities symbolically. So we've been working on the function notation. We started learning the basics of graphing calculator, including function notation, graphing lines, curves, points, sliders, all that stuff. And then we're going to do a little bit, get it started on constant rate today and Wednesday. So there's your kind of overall, that's the content of the exam. And then we had a quiz about a week and a half ago. I posted a blank copy. You got those back graded in recitation, right? So I posted a blank copy and then a full solution key for that. In addition, I posted solutions to most of the homework up till now. So if you just go back to assignments, in those items, mostly all the solutions are posted along with. So like where you got the assignment, now there's a version that's the solution. Okay? So that's going to help you with your studying. SUVs, all that stuff. Okay, so just look for to get the solution for for a particular homework, it's right by where you got the homework sheet. The procedure for taking the exam is the same as the pretest, the same as the PCA. It's going to be down in the basement of this building on Thursday. You need to be in the door between 10:30 and 6:30. You need your Sun card. You can bring a handheld calculator. And it will cover, so this stuff about graphing calculator. There will be test items about graphing calculator. So I may give you a few lines and have you interpret what that does. Or I may say, I want graphing calculator to produce this. What lines would you put in? Okay, so the basics of graphing calculator are on the exam. Any questions about the exam? Yes, sir?
Do we actually need graphing calculator?
No, there's no way that, not everyone has a laptop. So no, you won't need the software, but you need to know how to write out lines, handwritten, or interpret them. Other questions about the exam, which is this Thursday. Okay, and then you will not have recitation Friday. Okay, because normally recitation will be quiz day. We had Labor Day, and then we got graphing calculator kind of put us in a different mode at the beginning. But we're going to get into a mode where you guys have a quiz every Friday during recitation, and so the weeks of the exams we won't have recitation, so you'll be off this Friday. But we will have class Friday. We will have class. Okay, do I have all the homeworks coming in here? Is this all the reflections that normally due last Thursday or last Wednesday? So let's talk about the other part of the homework that was due today. Will this, if I hit enter, will this produce a graph? Why not? There's no y or x in it. So if I want the graph, what should I do to get the graph? If I put in, from now on, once I've established this function, from now on, what is it? If I invoke that function, what is it going to interpret as inside the parentheses, and what's it going to do with that from here on out? Whatever I put into that parentheses now, it's going to perform this set of instructions. It's going to take that, substitute it in for t, and perform this set of instructions to give us an output. In this case, would be expected attendance. Okay? So if I want to graph it, that means I'm asking for many expected attendances that I'm going to put on the x-axis. So what do I want? X. So x is reserved for all the values on the x-axis. So it's taking all the individual values, performing that set of instructions, getting the corresponding outputs, and graphing. And we want this graph to be from where? Up to 110? So now it's going to graph it. Okay, now I wanted a point. I wanted any point. I wanted to use the slider function to be able to graph any point. To get a point, remember, it's Control 2. So I want my slider is going to be n, and we want n to be temperature, right? We want n to be, I want to be able to choose the temperature and have it plot me that point. So how am I going to set up this point if I want to be able to choose temperature and have it give me the point on the graph? Yes, sir?
X would be n and then y would be a.
Yeah, x is our temperature, and if I want my slider selection to be temperature, it's got to be x. And what's going to be y? Okay. See how it's impossible to do this. It's impossible to plot this point without function notation. You got to have it because. So there was an earlier one where it said, for 80 degrees, plot the point. So maybe a lot of you, your first instinct was find a of 80 and put that number in there. Okay, but you can't do that here. You need that function notation to do this, right? Because n is going to change, and we need the corresponding attendance no matter what n is. Does it work? So we said that we're going to go from 0 to 110, 22 steps. You should have found that 22 steps will give you the points every 5 degrees. Okay, then I said put it on 25. So here's the point that represents at 25 degrees Fahrenheit. You get the corresponding expected attendance. What is the corresponding expected attendance at 25 degrees Fahrenheit? How would you respond to that? A of 25. A of 25, okay? And it would be the number that if you put 25 and put 25 into that formula, it would spit out what that value is. Something that looks like about 42,000. Okay, 42,000 at the game if it's 25. So now on number 9, it said we want to represent an increase in temperature of 10 degrees. We want to physically draw something that represents, starting at 25 degrees, an increase in temperature of 35, or an increase of 10 to get up to 35. Okay. So now we don't want to draw like a point, a diagonal line up to there. Okay. So what kind of segment in this graph would show just simply an increase in temperature of 10 degrees? What would that line segment be like?
Horizontal.
And how do we graph a horizontal line? So what horizontal line do we want to graph?
Y is equal to a 25.
Why does that give me a whole horizontal line and not just the same point that we got before? See, why does that give me a whole horizontal line?
Substituting a of 25 for all the values of y.
Okay. Substitute.
Substituting y for all the.
What is that? What is A25?
42,000.
It's a number, right? So I'm saying graph. If I'm saying y equals, I'm saying graph a constant value, right? Graph a constant value. No matter what the temperature is, it's just going to graph that expected attendance at 25. Now we wanted to show just starting here an increase in temperature of 10. So how can I do that?
An interval.
So the interval is going to start at what temperature?
Yeah, 25.
And go to? There it is. That represents an increase in temperature starting at 25, an increase in temperature of 10. Now we want, so what happens when the temperature increases by 10? What happens to the expected attendance? What's that? It goes up, it changes. Now we want to represent that change. So starting here, how can we represent that change? X equals 35. What's that? What does that mean, x equals 35? Yeah, so this point here is 35, comma, a of 35, and we want to show the corresponding change in height. So we said x equals 35. Do we want all of x equals 35? Okay, so here's the question. So this is great. This stuff is great because it's forcing you to really understand function notation. How are we going to get what we want? How are we going to get the visual that we want using graphing calculator? It really forces you to know the... So hopefully this, many of you were able to kind of think about that and figure it out that that's how we're going to get this. This change at x equals 35 starts at a y value of a 25 and ends at a y value of a of 35. What is the length of that line? Somebody knew. What's the length of that line and what does it represent? So what is the length of that line? Right there. Somebody knew. Yes, sir.
The change in attendance from 25 degrees to 35 degrees.
Okay. And how can we represent that? The length of that line?
And you do a of 35 minus a of 25.
He's saying the length of that is a of 35 minus, that's supposed to be a 3. He's saying the length of that is a of 35 minus a of 25. And that represents how much the attendance went up as the temperature changed from 25 to 35. Is this the same as a of 10? No. Is it the same as a of 10? What is, so tell me what a of 10 is. How would you represent it on this graph? What is a of 10? Tell me. Okay, so does the dot represent the quantity a of 10? What really represents the quantity a of 10? If we wanted to make it like this. Like, so you see how this represents the change in attendance? So what would a of 10, how could we represent the change? I'm sorry. The a of 10, how would we represent that? Yes, sir.
That would be your attendance when the attendance is 100.
And how could I represent that on the graph? It's not really, that value isn't represented by the dot, but what about the dot is the expected attendance for 10 degrees? Yeah.
Is the y value?
Yeah, so how do we show the y value?
Draw a line from the dot to the x-axis.
That's what it is. This right here is a of 10, right? So now look, is a of 35 minus a of 25 the same thing as a of 10? Totally different, right? Not only different in size, but different in idea of what they're communicating, what they're representing. The change in attendance from 25 to 35 versus just what the attendance you would expect at 10 degrees. So no, totally different. But it's just a really common thing that students say, or try to make that true, just because they think, oh, 35 minus 25 is 10. But really focusing on what do these values represent. You can clearly see that those are not the same. Okay, so for Wednesday, you're going to finish the worksheet. And here's what here's your end goal. Not only to be able to move the point with your end slider, but the calculus triangle as well. So what are you doing? You're taking that example that we just did, the one that was at 25, and now you're generalizing. You're generalizing the to any starting temperature. So not just 25 anymore. Not just 25 anymore, but as you move the slider, it will start at any temperature and give you that increase in 10 degrees and the corresponding change in expected attendance. Okay, so you'll keep that packet. We'll hand that in Wednesday. Save, once you get it, after all your hard work to figure that out and get that to work, save that for your study purposes. Save that file on your computer. Okay? Any questions on this? On the activity, creating the roving calculus triangle. Anybody? Okay, so go ahead and just have a pen out, pen or pencil. This is our quiz, as I promised. It's like 2 minutes. Real short. Need more? That's it. Okay, so just go ahead and write your name and your recitation time. That's all I need in the upper right hand corner. Just name and recitation time. Okay, so everyone's working by themselves. Pass left and right in the back. Are there any more back there? Any more quizzes? Pass left and right. They need them in the middle. Still need more. Who needs a quiz? Got one? Okay, one more minute. Okay, finish up what you're writing. Last couple seconds. Okay. Go ahead and pass it up. If you're done, pass it up. If not, you got 30 more seconds to write. Pass them up. Oh. So heading is name and 12 or 130, please. Stu. I have them all. Okay. So we're going to start talking about constant rate of change. It's the core idea of calculus. Okay? So we want to take our time, really know our way around this idea, because it's a multifaceted idea. There's a lot to it. Okay? So it's very possible to just reduce it down to a single thought or a formula, and then have lots of problems on that formula, and then move on. But we really want to think about it from different angles, different contexts, so that when we get into the harder stuff of calculus, our understanding of that's really going to help us. So let's do a review of the meaning of quotient. Okay, suppose quantity A has a value of 17, and quantity B has a value of 5. What is the meaning of the value 17/5? Okay, or 3.4 in terms of the quantities A and B. Find a partner. We're gonna have lots of discussion. So find a partner to talk to. Discuss this. What is the meaning of the value 17/5 or 3.4 in terms of the quantities A and B? Go.
I have a tendency of my mind's got their way off and things that I didn't figure that out. Yeah, I try to remember.
How much A
It's like we need a word. So I knew.
how many
Okay, 17/5 is what? Who remembers? What is 17/5? Anybody? Yes, sir.
There are 3.5 more 5s in A than there is B.
Okay, there are 3.4 more 5. So we really want to 5s in A than B. Okay, yeah, that's true. Okay. So what is that number 17/5? If that's true, which it is, what does the number 17/5 represent? According to quantities A and B, what is it? What is this number, 3.4? Yeah. Okay, well, what does it mean? Yeah. So that's the quotient. What's that?
How many B's you can fit into A?
How many B's you can fit into A? Okay. Other ideas? Yeah.
Like the scale from A to B.
Yeah. Okay. From
B to A.
Okay. Yeah. So when you say scale, you mean what? What does scale mean? Yeah.
Ratio?
It's a ratio. Yeah. But what is the idea of scale? Yeah.
The relationship between two quantities.
Okay. What relationship? What does scale mean? Scale is the right idea.
It's gonna be A is always gonna be 17/5 larger than B.
Right. Did you hear that? So it's 17/5 is. How many times greater? What? How many times greater A is than B? That's the idea of scaling. It's a scale. It's what you'd multiply B by to get A. It's how you would have to scale up B, magnify B, what you'd have to magnify B by to get A. Or how many times greater A is than B. Okay, then the other thought that was talked about earlier was how many of the quantity B would fit into A. Okay, and so that's the idea of that 17/5 it's really measuring A. It's really the size of A. But 3.4 is the size of A relative, right, in the units of B. Relative to B. So this is this idea of relative size. If I was measuring A in the units of B, it would take me 3.4 B's to get A. So it's the relative size of A with respect to B. So they're like twins. They're almost the same, but a little bit different. So it's what you'd have to multiply B by to get A. It's how many times greater A is than B. And so that's what the relative size is of A relative to B. Okay? So apply those two ideas and analyze this situation. I'll erase here. So it says, suppose every 40 milliliters of water poured in a container causes the height to increase 7.5 centimeters. So consider the quotient, 7.5, or the ratio, 7.5 divided by 40, which is this number, 0.1875. What's the meaning of 0.1875 relative to the volume and the height? So practice saying a good, meaningful sentence to each other. It's hard. We want to try to word it well. If you can word it well, then you really understand it. So go. Okay. Somebody new. What do you think? So how can we kind of apply these ideas up here to this situation down here? What is 0.1875? What does it mean? Yes, sir.
The rise in the height of the water relative to the volume building.
Okay, he said the rise of the height of the water relative to the amount of water poured in, volume of water poured in. Okay, exactly. Okay, so if we have some volume of water that we pour in, how much will the height rise?
0.1875 centimeters per liter. Milliliter.
Yeah, so I'm going to pour some volume in. Yeah, it was good. I'm going to pour some volume in. So how much does the height rise? Given that volume, how much does it rise?
0.1875 times that volume.
Yeah, 0.1875 of that, or about 19% of whatever volume I put in, that's how much the height rises. Okay? So that's the idea of relative size. The relative size of the height is 0.1875 of whatever volume I put in. Okay, what about this first one? Scaling. So how is it like a scaling factor? They're so close, but they're slightly different. So we want to understand it both ways. How can you talk about it as a scaling factor? Yes, sir.
If you started pouring water in, it'd be like, you could estimate it'd be like roughly about 1/5 of what you poured in.
What would be 1/5? About?
For every 40 milliliters of water, like if you know it rose like 2 inches or maybe 2 centimeters, then you can know it'll be like 80 milliliters.
Okay. So you're using it kind of the other way. You're saying if I knew the height, I could figure out what the volume was. Okay. So if I have an amount of volume, I could calculate the height how? Yes, ma'am.
At 7.5 centimeters, it's like 40 milliliters of its in, so you can calculate assuming that's
Okay. And so assuming that scale, so then if I pour any volume of water in, how would I calculate the height?
0.1875 is height per 1 milliliter.
Okay. So if I pour in any volume in, what would I do to calculate the height then? Times it by the scaling factor. This will scale. This is like a multiple. Our volume. This is the multiple of our volume that gives us the height, or what we would multiply volume by to give us the height. Okay. So that's a review of quotient, which is absolutely key in constant rate of change. So here's your quiz number 1. The 2 parts to the idea of constant rate of change. First is you got to have 2 quantities. You can't talk about rate of change with just 1 quantity. You got to have 2. And they're changing together. So as you change one, the other changes. That's the first part to the idea. You got to have 2 quantities. Second part is very specifically, how do they change together? Very specifically, changes in one quantity are proportional to changes in the other. Okay? So 2 quantities changing simultaneously, that's really kind of any kind of covariation. Constant rate of change is a very specific kind of covariation where changes in one quantity are proportional to changes in the other. Okay, we talked about this symbol delta. It's going to be really important for us. It means the change in a quantity. So we have this quantity y. Delta y is the change in y. Okay? So if changes in one quantity are proportional to the other, so if I have a change in x, that means that the corresponding change in y will always be some scalar multiple of the change in x. That's exactly what we talked about on the previous page in terms of quotient. So what is the quotient then? In this, right there, in that statement, which one of those 3 symbols, or 3 quantities, is our quotient? Yes, sir? K, right? So how do I solve for K there? What would K equal? Okay, yeah, I would just divide both sides by a change in x. This is what we already said. Every change in y is a multiple of its corresponding change in x. And if we wanted to get K, there it is, quotient. Right? It's quotient. Delta y divided by delta x. So every change in y has the same size relative to its corresponding change in x. That's what we said, right? And we also said that k is the number that if you had a change in x, you'd multiply by to get the corresponding change in y. So these were the two. Kind of statements we had on the previous page. Okay, so here's a bar diagram. Delta y and a corresponding delta x. What does delta y mean? What does that represent, delta y? That's an easy question. The change in our y quantity, okay? So where in this diagram is, say, the value of y, just the quantity y rather than the change in y? Where in this diagram is that? If the length of this bar represents the change in y, where in this diagram is, just say y? Yeah. Far left, okay? So something like this over here. So it'd be like another bar that had started over here, and we had the value of y like this. So we had some quantity y, and then we changed it. We increased it by this much. Do you see? And similarly, you know, maybe x was something like this. Who knows? So this was x. And then when we changed x, we changed y this much. So here's another set of delta y and delta x taken together. So here's delta y and delta x taken together. Here's delta y and delta x taken together. What does this illustrate? Comparing the first red box to the second red box, what is it illustrating?
Is there a greater degree of change in the first box than the second box?
Okay, so is the change different in this box than in this box? She's offering that up. Is that right?
At least for the y.
At least for the y. What is this intending to illustrate? That they're comparing these two red boxes. The changes are proportional. Is there something the same about these? So obviously, both the change in y and the change in x are less. That's how they're different. But is there something the same about these two? Yes, sir?
How they co-vary in each box of the y and x. Co-vary.
Okay.
X is half of y.
All right, so let's say up here, delta y. About how much is delta y given delta x? So what's the relative? What would we multiply delta x by to get delta y? What would you say? 2? It's not. Doesn't seem like 2 is going to make it. So what would we multiply delta x by? That's a little better estimate than 2. 2.3. Yeah, maybe 2.3. Or 2.5, whatever. So we'll say 2.3. So given a delta x, delta y is 2.3 times as much as delta x. Okay? If these are exhibiting constant rate of change, then what can you say about, in the second box, what can you say about delta y? Yeah.
It's the exact same thing. Delta y equals 2.3 of the change in x.
If these are in constant rate of change, she's saying that down here, delta y also equals 2.3 delta x. Would you agree with that? Yeah. How about here? What's that? Tell me.
The change of y is still Change of y is still equal to 2.3 times the change of x.
Do they look like they all have the same relative size to one another? Okay, so that would be displaying or illustrating constant rate of change because they all have the same relative size to one another. Okay, again, so constant rate of change. Every change in y is a constant multiple of the given change in x. Okay? Also, delta y has the same relative size to delta x. If those two maintain, then you have constant rate of change. This is what we said. Every change of y is a multiple of its corresponding change of x. Every change in y has the same size relative to its corresponding change in x. Okay, so let's get a context here. After a car goes under a bridge, it travels at a constant speed at 72 miles per hour, meaning that the number of miles it travels for some period of time is always 72 times the number of hours in that period of time. Okay, so if this represents constant rate of change, we want to really be able to identify what is delta y in this. So if you were to underline or circle a phrase in this little paragraph to identify what delta y is, what would you do? So talk to the person next to you. So what do you think delta y is in this scenario? Go.
The number of miles.
But J is a constant set into A and multiply it with 800 So I think change of y so I look at 72 as A. 72 varies in hours.
Okay, what do we think delta y is based on your conversation? It's good? What do you think delta y is good? Okay, so what phrase should I circle here that would be delta y? What phrase in the paragraph? Tell me.
My partner and I decided that it was the number of miles it travels for some period of time is always 72 times the number of hours.
So what? Okay, so
So
you want all of that or part of it?
Well,
Which is delta y?
yeah, just travels for some period of time.
Whoa. Sometimes this thing has a mind of its own. Okay. What do you think? Agree with that? Okay, so then what would y be? So let's take a step back and say, what would we say y is? Tell me. So what is the quantity y? So you've got the starting point from the bridge. So what is the quantity y? Way in the back. Okay, and how is that different than delta y? So we want to make the distinction between that and delta y. So number of miles traveled, okay. Which number of miles traveled? Because this is a number of miles traveled also. So that we got to really just make the distinction here. Yeah. Since it went under the bridge, is that what you're going to say?
At one point in time, not over.
Well, it has to be over. If we're going to travel miles, it's got to be over a period of time. So since the bridge. So we go some distance from the bridge, and then we might go some number of miles starting there, we want to go some number of miles, and that would be our delta y. Okay? What would delta x be? Yes, ma'am. Yeah, go ahead.
72 miles.
Okay, he wants 72 miles per hour. Agree with that? Delta x is 72. So remember what we said delta y equals what? Generally equals
Some constant times
k times delta x. So what will delta x be?
number of hours of some period of time.
Number of hours in that period of time. And what's k? That's our 72. So delta y, in this case, is always 72 delta x. If I go a half an hour, how many miles do I go?
36.
36, right? If I go 3 hours, there's 2 hours, how many miles do I go?
44.
The number of miles is always 72 times the number of hours, or that's the relative 72 is the relative size of my change in distance to my change in time. Okay? Part 2. So if driving after a while, the car travels for another 1.6 hours at a constant speed of 72. During that period of time, the number of miles the car has traveled increases by 72 times 1.6 miles. Same thing. What is delta y, delta x, and k? Go. Talk about it.
So delta y would be 1.6 hours, k would be 72, and then we change the x. So the delta y would be 1.6 hours. The first 1.6 hours. 72 miles an hour would be a constant.
In this scenario, what is delta y? Yes, ma'am?
The distance traveled in 1.6 hours.
Distance traveled in 1.6 hours, agree? Yep. Where's that? The number of miles the cars travel. Okay, what is delta x? 1.6 hours. Okay. Okay, and again, 72 is this quotient. It's the quotient of what? What divided by what? So is 72 a measure of distance or is it a measure of time? Is it a measure of distance or is it a measure of time?
It's a measure of time.
Measure of time.
It's a measure of distance over time.
It's either one or the other. Is it a measure of distance or time? Distance, how is it a measure of distance? It's not in miles, but it's in what? Measured in terms, in the units of?
Miles goes in an hour.
Yeah, so it's measured in the units of hours. It's the relative size of distance to hours. So it's how many miles you go in 1 hour. Right? It's also what you multiply the hours. It's the multiple of hours that you multiply by to get the distance. So for your homework, you're going to finish the packet. And then you've got more reflection questions from the chapter. Really practice. It's going to really force you to think about and practice, thinking about these ideas. What is rate of change, okay? See you on Wednesday. Mark